Okay students, let's start with a new topic, that is bending stress. That is the sixth chapter we have in this strength of materials, and this is the most conceptual topic which you will be able to see. Okay, now in bending stress we have basically two types of stresses. First is non-uniform bending and second is pure bending. So there are two types of bending which we can have. So what are these two types of bending? I'll show you. Firstly, what is a pure bending? The meaning is very simple. Pure bending means only bending. That's it. No shear force. So if the system has only bending, that is only the bending moment is created throughout the beam and there is no shear force which is occurring, we call that case as pure bending case. Okay? And if in a system we have bending moment as well as the shear force, that will be called as non-uniform bending. Okay, so firstly I'll give you an example of pure bending case. This is this case, pure bending, which I have shown here. I've taken a beam of uniform length L and it is uniform cross section EI and it is a simply supported beam and I have applied a bending moment, external moment has been applied, and here an external moment of M0 has been applied. So if I try to calculate the shear forces, firstly I'll calculate the reactions, that's what I do. So if I want to calculate the value of the, let's call this point as A, let's call this point as B. So if I want to calculate RA and RB respectively, so first equation will be RA plus RB is equals to 0. That's it. This will be our first equation. Second equation will be, because no external load is acting, we have external moments but we haven't got the external loadings. Now if I want to calculate the moment, summation moment at this point A equal to 0, so what I'll be calculating is M0, this is clockwise, I'm taking positive, and this is anti-clockwise minus M0. This will create, RB will create an anti-clockwise minus RB into L is equals to 0. That is the net moment at point A which I have done equal to 0. This gets cancelled and RB into L equals to 0 implies RB equals to 0 implies from this equation RA equals to 0. So what do we get? We get no reactions, and if we have no reactions, we will have no shear force because there is no external loading. So here we will have 0 shear force and that will be constant throughout the beam. And my SFD will be straight line like this. And here the system has no shear force. Plus what we'll be getting is, like here in the BMD, we have a constant bending moment. You can see here, M0. This is constant throughout. So here is M0. So this will be constant throughout the beam because this will be the moment. M0, first of all, here we will be getting the M0. There is no reactions or there is no support reaction which will change or divert this bending moment equation. So this will be constant throughout, and finally there will be an anti-clockwise moment, so we'll get this thing down. So that is what we have in our bending moment diagram for pure bending case. So we can see that bending moment diagram is constant and there is no shear force diagram, so which will be called as the pure bending case. Now let's look at a non-uniform bending case, which we all know, but I'll take an example which becomes a lot easier to understand. Okay students, now let's discuss the non-uniform bending case. You can see over here we have a beam in which load P is applied in the direct right hand side here, and therefore there is a shear force that will be generated because here R is, let's call this point A and this point as B. So here RA will be generated equal to P, and there will be a moment in anti-clock because this will generate a clockwise moment. There will be a fixed end moment that will be generated, that will be equal to MA equal to minus of PL. So this will be generated and therefore the shear force diagram will be constant P throughout the beam, and then it will come down to here, it will make it come down at the end. Similarly, we have the bending moment diagram. Initially we have MA equal to minus PL and it will be constantly tending towards this point. At the end we will have 0 bending moment, as you can see. Okay, so this is what we have in bending moment and shear force diagram, and this is for non-uniform bending case because here the shear force is there throughout the beam and bending moment is not constant as well. Okay, so this is what we have in shear force and bending moment diagram in non-uniform bending case. Okay, let's discuss now our bending equation, which is the most important thing in this chapter. Okay students, let's discuss the bending stress equation that we have, and let's try to derive that equation. This question is being asked a lot of times in our interviews, and lots of faculties and students focus on this particular thing a lot, because we have to basically, to derive this equation, we have to know some basic facts. Firstly, to use this equation, we need pure bending case. Why? Because when there is pure bending case, what happens is this whole beam bends in an arc of a circle and you get a perfect R. That is the radius of curvature of this whole beam. Okay, so when you have a designated R value of a beam bending, then it is only occurring only in the case of pure bending. So when there is pure bending, then only it will bend in the circle, arc of a circle. Now, next thing, here we have Hooke's law that should be followed. Hooke's law has to be followed, that is, we will take stress proportional to strain. But for deriving the first part, that is not required even. That is not even required. How? You will see. Firstly, I have taken this beam, now it is being acted upon by a load, so it now bends in an arc of a circle of radius r. So now, if I want to calculate the strain will be nothing but change in length, that is strain, which will be equal to delta L upon initial length. So here, as I can see that the change, here is the r, and this, if I go y distance below this neutral axis, this is my neutral axis, so if I go y distance below this neutral axis, I'll have this change. This is nothing but the strain developed or the change in length delta L, which is coming out to be y into theta. It's perpendicular, this is base, so we can take it as y into theta. And we know that initial length is what? R theta. So our change in length is y theta. And initial length is r theta. This theta cancels. So what we got is y upon r is nothing but our strain. So our first equation which came out to be is strain is equals to y upon r, and that will be giving us the first equation of the bending stress equation. That is, if I change the strain into stress, sigma by E is equals to y upon r implies sigma by y is equals to E upon r. This is my first relationship which I got because of this bending stress equation. Okay, firstly I considered a straight beam, it was acted by loading, so it got bended, and then we went y distance below the neutral axis, and that's what we got. This y is nothing but the distance beneath which we are considering in calculating the stresses at that particular point, and sigma is the stress at that particular point. Radius of curvature is r, and E is nothing but our Young's modulus or modulus of elasticity. Okay students, now let's move forward to try and derive the whole bending equation. So what I've taken is, at y distance beneath this system, this is my whole surface area. So beneath that I've taken a cross-sectional area of dA magnitude. So if I want to calculate the moment generated along this neutral axis due to this stress, so what will be the moment generated? This force that is coming out here and into that distance, that is y only. So what is that force? We have stress. If I multiply with the small area dA and integrate throughout the system, I'll get my bending moment, total net bending moment, and that will be nothing but m. That will be equal to integration throughout the area, and we have sigma dA, this is a force, and into y. So what is this? This is nothing but my equation for the bending moment which is calculated due to the whole system. So this is nothing but cos due to integral. Now before this I had derived that my sigma by y was equals to E upon r. So now I can replace this sigma, as this is a variable quantity throughout the section, so that I can replace this from this equation. So this will be now m will be equal to integral of E by r into y square dA. So E by R will come outside of the integral, that is as it is constant for a beam. This will be y square dA, and that we know that integral y square dA is nothing but our moment of inertia of the whole system. So this will be nothing but what? E by R into I. This is the moment of inertia about the neutral axis what we have. Simple cross-sectional area of rectangular, it will be BD cubed by 12. You very well know that. So now what I got is M by I is equals to E by R. And before I had E by R is equals to sigma by Y. So sigma by Y is equals to M by I is equals to E upon R. This is how you derive this particular equation. This you won't get in a lot of books. You won't get in any book in India, but you might find it in derivation in some foreign author books. But this is very, very easy and important to understand. How do you get the bending equation? You should go by the basics, and when you develop the concepts, then only you can apply in the questions which are asked in GATE or any examinations. Your concept should be clear so that you can get forward and write down those problems which are out of your thinking. Because if your basics are correct, you can solve any question possible. Thank you. Okay students, now let's look at the question from GATE 2004 asked from this topic, that is a homogeneous simply supported prismatic beam of width B, depth D, capital D, and span L. Span is given as L. Okay? Is subjected to a concentrated load of magnitude P. Full stop. The load can be placed anywhere along the span of the beam. Okay? They are saying that the load can be placed anywhere along the plane of the beam. Now, the maximum flexural stress developed in the beam. Now, we know that when the load is at the center, then only it will develop the maximum bending moment. And you all know that the maximum bending moment is nothing but when this is happening. You know that the support reactions come out to be P by 2 and P by 2. So now, the bending moment will be maximum at the center, and will be P by 2 into L by 2, that is nothing but PL by 4. So now we know that, very well know that, the maximum bending moment is PL by 4. Okay, this is the support reactions, supports which we have. And this is my BMD, this is positive, PL by 4. Now we very well know the bending equation, that sigma by Y is equal to M by I is equals to E by. Generally we solve the problem using these two only. So from here I get that sigma is equals to M into Y upon I. So as I know that the sigma is depending upon the M value and the Y value, because I is constant, because I is the nothing but the moment of inertia about the neutral axis that is fixed for the rectangular beam of width B and depth D. So what is that particular thing? So we know that that will be coming out to be B D cubed by 12, that is my moment of inertia I. Now, so what I want to do is, now I want to calculate my M value and Y value. I calculate the maximum, that is nothing but equal to PL by 4. Y will be maximum at this base or this one. So at the extreme positions we will have the maximum stress, and that will be nothing but Y will be equal to D by 2. So now everything is sorted. We have the every value. Now we have to just calculate the stress. So sigma will be equal to M. That will be M will be nothing but P L by 4 into Y, that is D by 2 upon what is I? B D Q by 12. So now this is coming out to be 3 by 2 P L upon B D square. Okay, generally I by Y, this I by Y is called as the section modulus. Okay, this is called as the section modulus. For extreme positions, this is nothing but I is equal to BD cube by 12 and Y is D by 2. So that is nothing but equal to BD square by 6, which you can directly remember. But this is valid for top and bottom positions, or you can call it extreme positions. This is nothing but called as the section modulus Z. Okay, so always remember this. What is the section modulus? This denotes the strength of a system. That is called as the section modulus Z, which is denoted by BD square by 6 for this particular rectangular section at extreme positions. Okay, thank you. Okay, now let's look at one famous question from GATE 1992, that is saying that the maximum bending stress induced in a steel wire of modulus of elasticity 200 kilonewton per mm square and diameter 1 mm when wound on a drum of diameter 1 meter approximately is equal to. So this is a drum which is having a diameter of 1 meter, and we have rounded it with another steel wire of 1 mm diameter. So remember the difference. This is a steel drum which is of diameter 1 meter, and then we have a wire that is of 1 mm diameter. Now if I cut this cross section over here, if I cut this and see this cross sectional thing of this wire, so we'll say that its radius is 0.5 mm. So it is at this distance. Obviously, the moment of inertia of a circular cross section is pi d power 4 by 64 about its neutral axis. Okay, so we can use this equation sigma by y is equals to m by I is equals to E by R. We need sigma, the maximum stress induced. So we know that maximum stress is induced at the bottommost point or the topmost point. That means that y is equals to R. That is nothing but 0.5 mm. Now here I have the radius of curvature also. This wire is bending, this whole beam, this wire can be constituted to compared to a beam. So it is compared to the beam and it is now going at a radius of curvature of R, that is nothing but equal to 0.5 meter, because diameter is of the drum is 1 meter. So it is constituting a radius of 0.5 meters. So we got the R value, we know the E value, we know the Y value, we can definitely get the sigma value. Okay, so my sigma will be equal to Y into E by R. That will be nothing but equal to Y will be equal to 0.5 mm into E is nothing but equal to 2 into 10 to the power 5 Newton per mm square upon R is coming out to be 0.5 into 10 to the power 3 mm. Okay, so now we can easily find out the answer, and this is coming out to be equal to 200 Newton per mm square. This is my final answer, which is very easy to calculate. Okay, so this is how we calculate this whole system. And if you want to calculate, this is a very famous question asked in many PSUs as well. So you can look after this question and the concept which I have shown you. Okay students, now let's look at the next question that has been asked in GATE 2016 set 2. Okay, the question is very simple, and what the question is saying is like a 450 mm long plain concrete prism is subjected to a concentrated vertical loads as shown in the figure. This is the figure which has been given. Cross section of the prism is given as 150 cross 150 mm. The cross section is given as 150 mm cross 150 mm, that is a square cross section. Considering linear stress distribution across the cross section, that is, they are saying that assuming bending equation is followed. That is what linearity means. Okay, the modulus of rupture expressed in MPa. Modulus of rupture is nothing but M by Z. I told you that I know that sigma by M by I is equals to sigma by Y. That means that sigma is equals to m into y by I, and that is nothing but equal to m into m divided by I by y, and this I by y is nothing but my z value, that is the section modulus, and this m by z is nothing but modulus of rupture, that is nothing but the stress. The stress at rupture is nothing but called as the modulus of rupture. So from there you get sigma is equals to m by z. Now I need m and z values. Bending moment for this symmetrical loading condition. How do you calculate? Very, very easy. See, this is a symmetric loading, so reactions will also be what? 11.25 kilonewton only on both sides. Okay, so this will go like this straight up to this point, 11.25 into 150. Now if you take any value here, the bending moment will be 0. Sorry, that will be constant, and that will be equal to 11.25 into 150 only, because the this value due to this loading is compensated by this value into this one. So these are compensated. So if you can check, if you take any x value here in this region, so my bending moment will be equal to 11.25 into x, okay, at this point clockwise, minus due to this one 11.25 into x minus 150. So what you'll get? You'll get 11.25 into 150, that is constant throughout, and then it will come down at this point. So this is the maximum bending moment that can be generated. So at this 1/3 span, I am going to calculate the cross-sectional area is taken at the 1/3 span. So 1/3 span I'll be going, cutting down the cross-section, seeing the dimensions 150 cross 150, I can calculate the z value, that is BD square by 6, that is 150 cube. B is also 150, D is also 150, this will be 150 cube by 6. So now I'll come here to calculate my modulus of rupture sigma, that will be m by z. So here it will be 11.25 to 10 power 3. That is nothing but kilonewtons converted into Newton, and this is 150 mm. So Newton mm divided by 150 cube by 6 mm cube. So this will be giving me 3 Newton per mm square, that is 3 MPa as my rupture, modulus of rupture. And this is how you calculate these simple questions. That is what the level of gate is. If you are clear with the basics, clear with the bending moment diagram, clear with the shear force diagram which I have taught you behind, you can solve any question that is possible in the coming chapters. This was all about bending stress. This is what they can ask you, not more than this. This is the basic concept, bending stress equation we have to remember, how to apply it, basic things we can calculate very, very easily. Thank you.